Now let's imagine a situation when you have a number of events based on the same experiment that are mutually exclusive and collectively exhaustive. Mutually exclusive means that they all are disjoint events. So if you choose any pair of these events, these pair are disjoint events, so they cannot happen at the same time, cannot occur at the same repetition of our experiment. And collectively exhaustive means that at least one of them always occur. So every time we repeat the experiment, at least one of these events must occur. And so mutually exclusive and collectively exhaustive means that only one, exactly one of them happens every time the experiment is done. Sometimes these events are called hypotheses. So they say there is a number of hypotheses about the outcome of the experiment. So let's denote these events as H1, H2, Hn. And let's say that there is another event, event A, based on the same experiment. So how this can be understood? Let me give an example. Let's say that 10% of all men has blonde hair and 50% of all women. For our country, it is true that because many women here in Russia dye their hair into blonde, and that is why share of blonde people among women is higher than among men. So I know I have this information. 10% of men and 15% of women are blonde, and I want to know what is the probability that a random person at the street will have blonde hair, no matter man or woman. So how I can find this probability? I should know proportion of men and women at the street. So if I assume that half of all people there are male and half are female, then I can say that probability to meet a blonde person is probability to meet a man, 1/2, times probability that this man has blonde hair, 0.1, as 10% of men are blonde, plus probability to meet a woman, 1/2, times probability that that woman has blonde hair, 0.15. So that is how, using this formula, total probability formula, I can find total probability of an event, which probabilities initially were given only for some particular cases, like men and women here in my example. So another formula that is usually used after applying the total probability formula is the Bayes formula, named after British mathematician Bayes. So you can see the formula. So it helps us to find probability of H given A when we know probability of A given H. So you have conditional probability of one event given the other one, and you want to find vice versa, probability of the second one given the first one. And so you can do this with the Bayes formula. And now we will discuss an interesting example where you will understand how we can get some interesting results applying this formula. And now I will show you an example that shows that the Bayes formula can help us to avoid serious mistakes our intuition can make. Let's say that you are going to be tested for COVID-19 disease using the PCR test. And let's imagine that this test is a very accurate one, very reliable one, so that for the person that has this disease, the test with probability 0.99 gives the right answer. And for those who are not ill with the COVID-19, it also with probability 0.99 gives the correct answer. So the test returns the correct result for 99% of all who are infected and for 99% of all who are not infected. And so you are tested with this test, and the test shows that you are infected. What is the probability that it is really so? What is the probability that you are really infected if the test shows so? You may say 0.99. You have just told us that the test gives the right answer with probability 0.99 for all people, for those who are infected and for those who are not infected. So the answer is 0.99, but it is not so. And even more information I have already given you is not enough to answer this question, to answer the question I have asked. Let us see. So let's say that we have two events, H1 and H2. H1 is that you are really infected, and H2 is that you are not infected. So this means that you are COVID positive, and this means that you are COVID negative. And event A is that the test says you are infected. So what I have asked you, I asked you, so the test shows that you are infected. What is probability that it is really so? So probability, I ask, is P of H1 given A. So A is given. You already know that A occurred, that the test shows that you are infected. And now you want to know the probability of H1, probability that you are really infected. So this probability can be found with the Bayes formula. If we apply the Bayes formula, so this probability is equal to P of H1 times P of A given H1 divided by P of A. So, to find this probability, we need to know P of H1, P of A given H1, and P of A, but P of A itself can be found only using the total probability formula. So according to the total probability formula, P of A is P of H1 times P of A given H1 plus P of H2 times P of A given H2. So we need these four probabilities, P of H1, P of A given H1, P of H2, P of A given H2 to find what we need to find. And so what probabilities I gave you initially when I asked you the question. So I told you that the test is a very reliable test, and with probability 0.99, it gives correct answer for those who are infected and for those who are not infected. So that means that probability of A given H1, so probability of test being positive, if a person is really positive, being 0.99, and P of A given H2, so probability of positive test if the person is negative, if the person is not infected, is 0.01. So actually what I gave you initially are these two probabilities. And as you see, to answer the question, we also need P of H1 and P of H2. We also need these two probabilities I didn't give you. So let's imagine that 1/2% of all people are infected with COVID-19. So that means that P of H1 is 0.005. And P of H2, probability of a random person being COVID negative, is respectively 0.995. So after we have these four probabilities, we can calculate what we need to find. So let's start with P of A. So I have a total probability formula, and I substitute these numbers: 0.005 times 0.99 plus 0.995 times 0.01. And this is approximately 0.0149. So you already understand that something is going wrong. So here we supposed that 0.5% of all people are infected, and here we see that 1.5% of all tests are positive. So probability of getting a positive test for a random person is not 0.5%, but 1.5%. So then let's find this probability I asked you to find initially. So P of H1 given A, according to this formula, according to the base formula, is 0.005 times 0.99 divided by 0 times 0.0149, and this is approximately 0.33. So approximately 1/3. So you have such an accurate test that gives a correct answer in 99% of all cases, both for positive and for negative people. And after being tested by such an accurate test, if this test says that you are infected, this is true with probability only 1/3. So it's very far from 0.99, you may think. So why? How it is possible? The problem is that so the test is very accurate, but number of COVID negative people is so very high that 2/3 of all positive tests are wrong tests of negative people. So number of people that are really negative is so big that 2/3 of all positive tests are their tests, are tests when it mistakenly says that negative person is positive. So this probability heavily depends on the real proportion of those being infected. If this proportion is low, like here, like 0.5%, this probability is also low. And so what do they do in practice? In practice, they repeat the test several times. So if something is, after being tested, if the test shows that someone is positive, they just repeat this test 10 times, for example. And if only one of these 10 trials is positive, so they say this initial trial was a mistake. And if, for example, 8 or 9 out of 10 tests are positive, so that means that it is really true. You can try to change this probability, change this proportion a little bit, and to look how this probability will change. For example, if not 0.5%, but 1% or 2% or 3% of all population are infected, how this probability will change. It's a very interesting task also.